aspetta, aspettiamo per un minuto, sarà forse il primo tocco della mattina.
Hello everybody. So here we have Alessandro, and he will tell us how to unleash free some of the proprietary data that you can find in some of the Italian PA. I don't know how to translate it. Thank you, Alessandro.
Good morning. Good morning. So my talk today is about how to translate proprietary data, geospatial data, into more standard formats so that they can be actually used together with the usual tools and usual systems. Apparently there are quite a lot of data in Italy for sure, but also abroad that have particular format that is not what you would expect usually. And the way to translate that to standard formats has some common features, and I will use the official Italian cadastre data, that is the legal definition of properties in Italy, which is distributed by the Italian institution in a proprietary format, and using that as an example to see what support Python and open source libraries give you to do the translation. So first of all, the geospatial data formats are quite hard because the problem is quite hard. You have what you need to describe is our position on the grounds. Since the grounds is 2D, you have to do some kind of projection. There are thousands of projections in the world because every nation have one or more projection systems that are very useful in that region but maybe not in others. So you need to have to describe, in order to have a geospatial format, you have to describe the reference system with projection, ellipsoid, and unit of measure, and then you have different kind of shapes and geometric relations because you may have vector data or grid data or raster data. Vector data can as well have points, line, and polygons, and also the multivariants, that is multi-polygons, multi-lines, and all of this may be embedded in your format in the most strange ways. And then usually you also have structured data, that is some DB-like, some field data types, some field data embedded in field data types that are associated with each geometry, and these are called features usually. Just to give you an idea of how many possibilities there are, just the text data alone, whoever has done any web development knows, it's not that easy, because you have a lot of encodings to translate text data into binary format, and from the easy 7 bits to all the 8 bits and 16-bit variants. And it has emerged a standard format, a good standard, that is the UTF-8. It's what is largely used now, but if you have to do with legacy data, you need to know how to detect and how to handle all the other formats. Now, this is also true for geospatial data. As a matter of fact, that complexity is just a tiny bit of the whole point. More or less, each of the things cited here may have as much complexity as the single text data. That is, there are a lot of ways to personalize, to internationalize or localize what you are what you want to describe. So what is the objective of this talk is to learn how Python can help you do a translation. That is, you start with the custom proprietary geospatial file format that most probably is application specific or legacy. And your problem is that it's not supported by usual widespread tools, that is ArcGIS or QuantumGIS or PostGIS, all the stuff that you usually you want to use to process and to display your data. The fact that it's not widespread, it means that it is possibly that even if you get a specification for the format, the material format, that is what you usually get in a file, will not match exactly the formal specification. So you have a material format that is different from the formal format, and this makes translation much more difficult because you cannot just follow the specs. What you want to obtain is a standard geospatial file format that is general purpose. You can interoperate with whatever tool and put the data on the same map with other data that you have. And this means that you want to get something that is well supported by widespread tools. Just to define what is a good file format is something that uses some easy spatial reference, easy way to codify the spatial reference system. There are a few. You can use well-known text or a number from the PSG catalog or Proj4 strings. You want to embed your data into some kind of format that is, in particular for vector data. An Esri shapefile is the most common, but also GML or KML, or you want to put your data into PostGIS. So this is where you want to reach. You start from something that is very custom, and you want to reach here. So you need to write what is called a translator. The translation is really a translation. That is, you may choose whether to do it more strict or more liberal. It's not always easy to match the information in your proprietary data to a geospatial format. You have to make choices, and choices are not always, they just can cover a subset of all possible uses. You need to start a format specification, a lot of data of test files, possibly coming from different data providers. This is because you must be aware that data providers may not implement the specification as is written. Or maybe the specification is ambiguous or incomplete. This happens. And then if you have access to competing implementation of the translation, it's a good way to see if you are getting the right results out of your test files. Then you really need an unhealthy dose of masochism, because it's really hard if you get the common implementations don't support the specs exactly as it is. And it's really it's a pain to quite often to do this kind of translations. As an example, we have written, so we have quite some practice, we have written a translator for the CXF format that is used by the Italian administration to distribute the official parcels of land definition in Italy. What you want to, the data is, once you get the data out, it's look like this. The lines are the boundaries, and the polygons are the parcels of land. That means the unit of land that are taxed and can be sold as a unit. You also have, I'm not sure if you can see it, some of the smaller polygons are red border and are shaded inside, and those are the buildings. And they are in the same format, so you know how the land is done and how the buildings are laid out on the ground. This file format is done by a set of formatted text files. It has the data, the geospatial data is embedded there in quite obscure spatial reference system like GDALOGR or Cassini-Soldner. The main point, one of the main challenges is that it has, the Cassini-Soldner is actually a local projection. That is, you don't have a definition of on wide regions. You might have small regions with a local origin. And in Italy we have more than 800 local origins. And so there are some big origins like this one and a lot of small origins. So it means that if you get a file, a data file that is somewhere here in Piemonte, you need to look up where is the zero of your projection. Among the challenges is not just that there are 800, but that they are not freely available. I mean, the positions of the local reference system is not in the public domain, so you have to buy either data or to ask to the administration, but they will not give you a batch of results, just one after the other. Then there is also another challenge, that is that this stuff has low accuracy in position and orientation of the geometries. These are all data that have been built historically, measuring the distance between points. So it has decent accuracy on if you are close to the points. That is, the polygons are more or less how the shape they should be. But then the whole file may be translated and may have a rotation even. And at the global level, you may have errors of 100 meters. So you have to include a way to correct the data before you can actually use it. So we did write a translator for this kind of format. It's a library. The command line tools are not yet really polished, but it's useful. We have used that in production, and we could use we could do the translation from this rather uncommon and obscure format to standard formats. What we have done, and here I try to present it in the more general way, is this process here. First of all, you need an input step where you do something that is extremely custom for your format. You have to parse the data. In our case it was text, in other cases it might be a binary blob. So you have to use whatever you have, mostly Python standard library. If you're lucky, you can get a library, a format-specific library, to get what is written there and to put it into your data structure, into your Python data structure. After you have extracted that, you have a few steps, a few processing. The processing step is done of a few sub-steps. First of all, if you want to have a different projection, you have to project to reproject all the spatial data. This is done very consistently with Proj4, and there are a couple of ways to access it in Python. And after that, you have to make quite a few choices on how to arrange geometries and structure data within your new file format. You are trying to get the old data in a way that it's you want to conserve the meaning, the semantic of your data, but put it into a shapefile, for example. And in this case, for example, in the input data we had lines and points and polygons all in the same format. Instead, for shapefile, you have to, or for database tables, you are supposed to separate the various types of geometries into different files or different tables. And then you may do some high-level processing to check that data is consistent. And this is also, it can be done quite easily in Python. Now, the main point here is that the GDALOGR library gives you a quite nice abstract way to describe geospatial data. So if you use it at this step, if you use it, the structure that are in the semantic structure that GDALOGR gives you, it will be really, really easy to do the final step. That is to choose a file format of your liking and save the data in that file format. Now, the input step, it's mostly custom. There's not much that that can help you from the Python geospatial tools. You just have to try to follow the specs, the specification that you have, read pieces of the data one after the other. The most important point is try not to get lost, because you may, if your implementation is incorrect or the data is incorrect, you can try to skip to the wrong place and you don't understand anything after that. It's important to validate very early, that is, especially during development, and you need to know immediately that something is going wrong. There are usually in this format some redundant data, and you may check that everything is consistent and so on. And most of the time it is possible to skip part of the data, and especially at first you better try to get the frame working, that you can actually read all the data, even if you don't parse actually bits of the data that are not immediately interesting. Now, the main point here is if you have a data that is widespread enough and its specification, it's not really, the file that you find in the wild are not really close to the formal specification, you need to be very careful when you raise a format error, because it might be that the data contains the data. It has interesting data in it. You could use it, but since it doesn't follow precisely the spec, or maybe you interpreted the specs incorrectly, you don't want to bail every time there is something that is wrong. You may just go on, say, there is something that I find unusual, but I try to pass the rest, so that if it blows up, because then you do some kind of wrong read, you know where the problem is, but you still try to parse the rest of the data after a format error. Now, this is instead where it starts getting interesting. That is where you can use some tools, some Python tools, and open source, that will help you in achieving the result. The first point is that you need to define the source and target system of reference. This is already not completely trivial, and the Proj4 helps you both doing the definition and doing the reprojection, that is the hard work of turning the coordinate value in one reference system into the coordinate value of another reference system. In our case of the CXS files, as I said, we have these quite obscure projections that are not very useful once you want to use the data together with other data. And we have this problem of the origins that must be supplied by the users. User must, when a user gets a bunch of files, he must also get the latitude and longitude of the origin, of the local origin, so that you are able to place correctly the bunch of files. Then, if your data can benefit from it, you may even apply custom correction more or less at the reprojection step. In our case, this was quite important because, as I said, we got even up to 100 meters of errors, and obviously that was quite visible even at a large scale. The problem here is that there's no other way to get the parameters for the roto translation than to get the data, get it out, compare it to some other reference data, then try to do the translation, and then you have the parameters. Once you have, you can do the translation again so that it's inserted at the right spot. Now, how do you get this done in Python? This is not actual code. This is just a shortcut for, a sample of the code. What you use here, what I used here, is osgeo.osr. This is part of GDAL, of the Python binding of GDALOGR, and it has two classes that are spatial reference system and coordinate transformation. In the case of the Cassini projection, which is not really known, you have to use the direct Proj4 string. This one here is how you describe a projection, a custom projection to OGR. You need to insert the latitude and the longitude of the origin, and we leave it as a template so that we can pass it the numbers that we expect the user will give us. So we instantiate our source spatial reference system, and we import from Proj4 the proper string with the custom origin. Now this is ready to be used for the translation. In the case of the target spatial reference system, that is which reference system we want the data to get the output, we can do something slightly easier, that is to just use one of the EPSG numbers, because we are interested in getting the data in Gauss-Boaga Ovest, which is yet another quite obscure spatial reference system, but it's very used in Italy. It's widely used in Italy. So these are two ways to initialize a spatial reference system. Then we instantiate the coordinate transformation. It's very easy. And after that, we are ready to do the work. Do the work means that at some point in the code, whenever we get the coordinates of a point on the original reference system, we have first of all to apply a user-supplied correction. That is, this can be arbitrary, and in our case it was a roto translation, which is quite common, but could be anything. Once you have the corrected, once you have the coordinates of a point in the corrected source system, it means that now they are placed in the correct position in the original reference system. Now we can do the transformation. The only point to be that you need to check here is that we are using, we assume that the points here are 2D, while the transformation point method assume that they are 3D. So if you here we just give two the x and y, so it assumes that the height of the point is 0. But then we have to truncate the result, because the result will be 3D and we don't need the height. And this is the point it's translated. Note that this transformation point, this method, can do really a lot of work, because the translation the two reference systems may be on different ellipsoid. They go from degrees to meter, or it's really a lot of work is done here, and really a lot of fine details are taken care by Proj4, and we should not care. It's a great, really a great library, and it's widely used, widely tested, so you can quite count on it. So second part of the processing step is to decide how to arrange the geometries and the structure of data. And you usually should group geometries into layers that are homogeneous by type and semantics. By types is point, lines, and polygons. As I said, we have all together in the input file format, but we want them to be on different files, on different shape files. And then you may have also for different layers. For example, bordi, it means they are all the polygons that for buildings and for land parcels. But fiduciali and symboli, they are both points, but different in semantics. The fiduciali layer is some points that are recognizable on the ground and have a position, and the position is recorded in the file, so that people, when they go and try to measure, they will not measure really from the origin, but they will look for the fiduciali that are close by. They will say, okay, they are in this position, so I'm 5 meters over from them, and this is where I am. But symboli is just a way to add symbolic information to the map, so the semantics is totally different from fiduciali, and even if they are points, I put them on a different layer, on a different shapefile. And then you may add fields, because sometimes you don't want to map, you don't like you want to add stuff to each record, so that it's more useful once you use it together with other data. And you can perform higher level processing and validation at this step. Now, how GDAL, OGR, and Python help you doing this stuff? So we have a bunch of imports that are all from OSGeo OGR, which is the main module for treating this kind of the vector data. We can choose any target format that is supported by OGR. There are probably 15, 20 or more file formats that are supported. SV shapefile is the most common one for files, but then you also have PostGIS if you want to put the data in a database immediately. In order to create the output file, you instantiate a driver, and you create a data source. You ask the driver to create a data source with a certain destination. Now, destination in our case will be the name of a folder, and every layer will be a set of shapefiles inside the folder, because in this way we can have more layers within the same shapefile, folder-like shapefile. Now, as an example, we build the fiduciali layer. So we add a layer whose name will be fiduciali in the data source. We set explicitly the target spatial reference system so that it will be written in the file. So that after that, all the data will know how to interpret the numbers, the coordinates there, and we declare it to be a point. Here we can add any number of fields. In this case, I just show two. One that is not, it's some kind of file-wide name, comune. It's the administrative region where the feature is, and the number. It's the counter of the fiduciale. So how you create them, you have to instantiate a figure with the layer definition, with the proper layer definition. You have to set the various fields with your data. You do the projection here using the source to target that we defined in the other snippet. So we can create a geometry. We have to set the geometry, the x and y and z of the geometry, and then we add the geometry to the feature. So the feature now represents the geometry with all the data, the record-like data that we added. And then we just create the feature inside the layer. Now, you have to do this, obviously, for every feature that you are interested in. And when you get out of when you finished your work, you just can do data source destroy. GDAL usually puts the data while you are working, puts the data on disk while you are working, and when you do the destroy, it just flashes the rest of the data to disk, and you have your standard file format ready to work. Note that here you don't see anywhere any specific of the output file format, because everything is handled by OGR, and OGR presents to you an abstract layer, and you have just to work with that abstract layer. This means that if I can change the target format to a lot of other different formats, and this stuff will just work. So as I say, the output step, it's very easy in this case, because once you have that, you can just close it, close the file, and you have translated your data according to your model into a set of shape files or whatever that now are ready to be used outside of with whatever other geospatial data that you have. A brief summary. Python geospatial tools are quite powerful. They are used in real life quite heavily. And the GDALOGR and Proj4 are C, C++ libraries, so you have bindings in a lot of other languages as well. And they are the workhorses, the ones that do really the work. But Python is one of the most used languages for accesses those services. Recently, I started to be interested also in Shapely and Fiona, which are two ways to get more Pythonic access to GDAL and Proj. It's the same machinery, but with a much more Pythonic. I don't know if you noticed, but it really felt like writing C++ or even C with Python. It was not really Pythonic what we did. And Shapely and Fiona tried to make all of these little things much more Pythonic. And they're very nice. They're not as actively used, but I invite anybody who is interested to look at it, to look at them, because it's really nicer to use them. So, thank you. I hope I show you how Python and open source software help you translate wired geospatial file format to something really useful. Thank you.
Thank you. So, any question?
How is the performance in Python compared to in C? Because I mean, a lot of this kind of work tends to be just a loop over a bunch of points, and in Python, then you're going to have the Python function call overhead, and that's going to be pretty significant.
It depends on, obviously, on the size of the thing that you are doing. Usually, this is anyhow a translation that you do once, and not that you do usually. So performance is not too critical. I mean, if you have, it's not that bad. I mean, I could translate big data, and the translation part was not really the bottleneck. The bottleneck was doing the consistency check in the Postgres, so in PostGIS. So it's not really significant, the impact. There are ways to do faster than this. For example, you can transform a bunch of points, not just 2 points. It is supported. Anyhow, even if it's slow, you just do it once, and then once you have the data in a reasonable format, you can translate them with the GDAL translate, for example, or OGR to OGR in this case, which is done in C, and it's much faster. So it's not that bad. It can get better, but it's not really significant as well.
Any other question?
Yeah, hello, my name is Gauta. I'm from Norway, and we have a similar format there, and I've been processing quite a lot on that. And one of the problems I've met is that people don't make the text files following the defined format. The solution I found, instead of handling the exceptions within the code, I did a cleaning of the data before I even tried processing it. Is that something that you've looked into too?
Not in this case. I absolutely feel your pain, because we had similar problems. Fortunately, in this case, the data provider, the main data provider, is just one. So they may have a different version of the code, and they may have, different procedure in different offices, but more or less the data provider is the same. So for us, the bigger problem was to understand which part of the specs were not followed precisely, but then it was always the same. So we could just adapt our code to the material format, not to the formal format. And in your case, I think if you find a way to pre-process the data, fine. Otherwise, what I suggest is not to be too picky about the formal format. I mean, just write an exception if you lose control. I mean, if you're lost in the file, then okay. But otherwise, just try to go on and see if just print a warning that is important for debugging, but go on and possibly implement in your code the non-specs. I mean, something that is out of spec, but it's how the file looks like.
One last question.
Hi. Did you try to do any topological validation with this data? And if yes, how?
Yes, this is what I said here. Higher level validation, processing and validation. Topological validation. In our case, fortunately, there was no problem. But the specification was not precise. I mean, was not clear, so that it was not clear whether polygons were closed, but they were, so everything worked. But I mean, we could have had to close them ourselves, and it was not indicated the rotation, the direction of the polygon. They could have been in the opposite direction, which is not how the OGC geometries are done. So we were lucky. We didn't need it. We only did topological validation after inside the database, just doing an isValid inside the PostGIS. But OGR and Shapely give you access to Geos, which is the workhorse for doing this kind of stuff. So topological validation and everything.
Okay. Thank you very much, Alessandro.
You're welcome.
Grazie.